Today we're going to do section 4.5. So first, let me show you the book, okay? Specifically the bottom part, which we already showed last time. Okay, that's that. Next, page 136 and the 137. So let's see if I can get this to come out correctly. Okay, let's see. First, the screen, like, okay, that, I guess that's close enough. All right, and then a little bit closer on top. And a little bit closer on the bottom. Oops, did I do the top right? Let me check again. Okay, that should be good enough. Next, this is page, I don't know what page, 138 and 139. Okay, that should, let's see. Okay, that should do it. Maybe move over a little bit. Okay, and then a little bit closer on top. And on the bottom. All right. Finally, page 140 and 141. Let's see. All right, let's make this thing. Let's see, somewhat parallel. All right, and then a bit closer on top. And a bit closer on the bottom. Let's see. That's good enough. So let's start on page 135, section 5. First, there's a paragraph up here, which the introductory paragraph. Please read this yourself. Basically, we're saying that the Lagrange multipliers are designed such as a neat trick designed so that when we have a hard time deciding who's the independent variable and who's the dependent variable when we maximize or minimize some problem, then the Lagrange multiplier comes in quite handy. Now, the Lagrange multipliers was taught in Calculus 3. If you don't remember it, it doesn't hurt a thing because we're going to develop it here from the ground up. Okay, so let's look at the bottom of the page where we have a function, right? Let's call it u. U equals f of x, y. It's some kind of a function, and we need to maximize this thing with turn to the page, next page, where it says we need to maximize it where x and y are connected by some function called g. And we have done this before, okay, even in this book, right? And then there are conditions. Specifically, you notice that f and g better be have first continuous first partial derivatives. But more importantly, g1 and g1 squared and g2 squared is bigger than 0. That just means one of them at least is not 0. Okay, if they're both 0, then we got a problem. Well, anyway, so that's the basic condition. Now, if this is the case, then we can do what we've done before. Here is the trick we pulled in the past. What we did is we have such a function, right? So what we did is we do the implicit differentiation and calculate. Let's say y. We'll pull one of them as the independent variable. Let's say y is y of x. Then we dy by then g1 takes partial differentiation. We get this equation, which gives us what dy by dx is. And then we are going to calculate, let's see, let's plug it in here, y plugged into u, and then we're able to do du by dx, which becomes some part of with dy by dx in it. Plug it in, okay, we did this in chapter 1. And then we get this equation, which becomes this equation. This equation is the same as the Jacobian. Okay, and so that is how we used to do this kind of thing, which is fine. But now we are gonna pull a new trick. Okay, the new trick is as you can see, this to derive dy by dx, you have to assume that g2 is not 0. Okay, and then so then what we're gonna do with the Lagrange method, the multiplier method, is this. First, we'll define a function v. Okay, the function v is f of xy plus lambda g of xy. What is it? Well, that's the same. Then the function v is the same as the function f. Why? Because g of xy is 0 all the time, right? So then it doesn't matter. So adding it doesn't change anything. So v is the same function as f. However, when you take the partial derivatives of v, then you get these things, okay? And then what happens is that when we solve from this equation, we have the partial v with x and y, and then from these two equations, if you set them equal to 0, then that would be where partial f is going to be 0. But in the meantime, you can calculate that lambda is going to you can calculate lambda to be that thing, and then plug it back in. I mean, this lambda comes from the first equation, then you plug it into the second equation, and you get this thing, which is identical to what we had before. See, so as a result, the Lagrange multiplier is the same thing as we've always done, except that now there's a neat trick. We have a lambda there, so we have another variable. Now that actually comes in very, very handy, okay? Sometimes, not all the time, it's not guaranteed. But sometimes it really saves a lot of work, because then you don't have to do a lot of division, and then when you take the partial derivative, your entire derivative just blows up into a giant mess. In those cases, the Lagrange multiplier trick really works. But as you can see, that is how this works out. Okay, and so they are all equivalent. Now, as we will therefore conclude this solution as and so please work all that out yourself too, okay? But the conclusion is, as we have seen on the bottom of the page, theorem 5, where we have f and g is in C1, and then g1 squared plus g2 squared has to be bigger than 0, so one of them at least isn't 0. And then we can do this lambda trick. There's the first one and the second one, and then the original g equation. So then we end up with 3 equations and 3 unknowns, and then they are often easier to manage than the old way. So that's what we're gonna do in this section. Now let's look at the next page on top, where it mentions that this theorem, we should say that is in the domain D. What's a domain? Domain is an open set, okay? That is, which means we're not considering boundary right now. Things happen weird in the boundary, and we are only concerned with the interior points, whether it's a maximum or minimum. We're not considering boundary at this point. So let's look at example A, which is a quick little example. We need to find the rectangle of a set perimeter, which has but we need to maximize the area. All right. Now to do that, we have let's see. So please do this yourself, okay? It's very straightforward. And we have f of x, y, and g. Then so v as defined is f plus lambda g. And then we take the partial derivative of v. We get this one and this one. And so we got 2 equations plus the g itself, so 3 equations. And then from these 2, we quickly notice that x and y are the same. And so if x and y are the same, plug it in here, then you notice that what x and y is, they have to be L over 4, which means the area must be a square. So it's a quick, easy example to demonstrate the Lagrange multipliers. So please do that yourself as well. Now next, let's look at example B. Now please make sure you do example B yourself, because example B is odd, okay? Now the problem itself sounds reasonable enough. We need to find the shortest distance from the point 1, 0 to some parabola. That seems simple, right? So we have the 2 functions. U is x minus 1 squared plus y squared, of course. And then y squared equal to 4x is the condition. And so normally in the past, as we done in the past, we might plug in y squared equal to 4x into the equation in u, and then we'll just calculate du by dx equal to 0. We don't have to worry about Lagrange multipliers, right? Except that when we do, we will find something odd happening, that we'll find the x equal to -1, which is not acceptable because x has to be positive. I mean, x equal to -1 is just not going to happen. Okay, and so that is so weird. And why is this happening? The reason this is happening, if you pay attention carefully, is because of to substitute stuff like that, we require G2, that is the partial derivative not be 0. And the G2 here is indeed 0 when you define G equals to y squared minus 4x. Okay, when G2 is 0, then du by dx is not going to come out properly. And as a result, the whole thing is falls apart basically. So I mean, the original, our old method turns out to not work. And I've also graphed this thing to show you what it looks like. Okay, here's the graph of this thing. As you notice that on the other side, we have the substituted equation right here. When you substitute y equal to 4x, you notice it does have a minimum at x equal to -1, but that has nothing to do with the minimum we're looking for. The minimum we're looking for is actually right here. So so the whole thing is quite weird, and it doesn't, more importantly, doesn't work. However, the Lagrange multiplier method does work though, because if you plug everything into the Lagrange trick, because the Lagrange doesn't require G2 and G1 to both be not 0. Even if one of them is 0 is okay as long as the other one isn't. So and when I say this is 0, I'm talking about at the minimum point. So things might kind of look weird here. Now, so let's apply the Lagrange multipliers following the rules. Okay, then we have v equals f plus lambda g. You calculate f1 plus lambda g1 and f2, and then mess around with the equations. You quickly come up with y equal to 0 or lambda equal to -1. Now lambda equal to -1 will give you an odd result, that is x equal to -1, so we reject that and we stick with y equal to 0, which means x is also 0, and therefore the distance is, when you plug x and y equal to 0 in here, the distance is exactly 1, and that is the right answer. Now, on the graph, that means that means the graph, see, these are the original equations, right? This is the function f, and that is the function g. So you notice that when they intersect, the lowest point is exactly, well, right there, where the function, the function is should be equal to, well, whatever that point is in this case is x equal to 0, y equal to 0, and z equal to 1, see? And you can plot this out yourself as well. So anyway, so that makes a quite an interesting illustration where our old method doesn't work, but the Lagrange method works anyway. So that is pretty nice. So normally in the example where we run into a mess, we will try to use the other variable as independent. That is, which will be much harder in this case. That is, plugging y squared. Okay, maybe not that much worse. Plugging y squared in here didn't work, so maybe we should have plugged in x equals y squared over 4 in here and see how that works out. But we don't have to worry about that with Lagrange multipliers because it takes care of both things at the same time, essentially. That's why the last sentence of this page says that the strength of the Lagrange method is in not singling out any variable as independent is thus brought to our attention. Okay, and so that is where the benefit is. And it doesn't always have a benefit, but sometimes is useful. It really depends on the situation, what you're maximizing and how the formula works. Now, so let's look at the next page. I'm on page 138. Now we have the same problem, but with 3 variables, okay? And so now, but everything goes more or less the same way. So if we have 3 variables, then of course we have the original function, and here's the constraint function, and then we require that the constraint function has at least one of the partial derivatives are not 0. Now if that is the case, then we'll work something, the way we did it in the past is this. Let's see, I think this is it, yeah. So the way we did it in the past, what is that? Sorry, give me a second. Okay, I think I found it. It's down here. Now, the way we did it in the past is that we have the function, and then, no, this is still not right. Okay, the stuff on top is correct. Okay, so we have the function, okay, the f and the g. We'll do it the same way as previously with the 2 variables. That is, we define v as such, okay, and then take the partial derivatives. This time we have 3 variables, so we'll take 3 partial derivatives, okay, we end up with 3 of these things. And then we'll solve for lambda from the first equation, plug it into the other 2 equations, and then we end up with some stuff. Okay, that looks basically the same as, see, this is basically the same thing as what we had before. Sorry, I think I showed you the lambda first. No, you're supposed to see this first. All right. Now, we have 2 functions. What we do is, well, before we do the Lagrange multiplier, okay, this is our old trick, right? If we have 2 functions like this, we'll pretend as one of them is the independent variable. Let's say z is equal to zxy. And so we require g3 not be 0. And then we take the partial derivative like this, right? And also take the partial derivative of both f right here and g right here. From g, we're able to come up with what is the partial g partial x, plug it in here. And then we get this particular equation, which equal to 0, which can be written like this. And similarly, we can also get, that's just from partial u partial x. So the next thing we're going to do is partial u partial y, which eventually will get up something like this. So in any case, we end up with two Jacobians, which is exactly what this says. Okay. Now, so I did the z one, but I skipped the others, but they are symmetrical, right? Because our function is all symmetrical, and so that's the old method. That's how we used to do things. All right. So let's see. Let me show you this again. I think I've gone through a bit haphazardly. But the point is that we just go through the same motions that we always done. So please do this yourself as well. Okay, and make sure that, well, I know we've done it many times before, but it's been a while, so it doesn't hurt to do this once to refresh your memory. Anyway, so that is how this comes out. And with that, then now we can do the Lagrange trick. So now with the new method of us going into the Lagrange multiplier is we do the same thing as we did previously with the Lagrange multipliers, and then solve for lambda in one of them, plug it into the other 2, and if we do, we end up with the exact same Jacobians we got before. We'll end up with this and that Jacobian for yeah. Well, anyway, so, and that's why the Lagrange multiplier works. So the point is that if you calculate lambda from the first equation or the second equation or the third equation and plug it into the other two equations, then you end up with you will end up with these 6 Jacobians, okay? And so to show that this formula works out, see, everything checks out. So please do this yourself as well, okay? And yeah, there is to make sure, well, at least do one of them. I mean, it's not, I don't think it's necessary to do all 3. So at least check, say, this one by, I don't know, well, pick one of them. What you're dividing, but anyway, it will come out. If you check one of them, doesn't matter which one, lambda and isolating lambda, and then you can notice that the equations all come out identically. Then you end up with the same kind of equations like that. And that's why the Lagrange multiplier works for 3 variables. And this is how we normally do it. And so let's look at the example here. Okay, example C, where we have a rectangular parallelepiped, which means a box. Now the surface area is fixed, and we need to maximize the volume. Then, of course, this is a standard problem. Okay, we will maximize x, y, z, and then whereas the condition is the 2 times all those areas equal to minus a squared equal to 0, or they equal to a squared, either way. So we plug in the v and follow the rules, calculate vx, vy, vz, and we have this stuff, okay, a bunch, 4 equations and 4 equations, 4 unknowns. So we manipulate them. Let's consider equation 1 and 2. We get this, and what does that look like to you? Eventually, you multiply them together and realize x equal to y. Okay, on the other side over here, and so then you realize then, well, similarly they're all symmetrical, so z has to be y as well, so they're all the same. And if they're all the same, you can plug into the area formula and quickly figure out that the x, which is the same as y and z, equal to a over square root of 6, and yeah, and the whole thing is a cube, of course. So that is one sample of how to use Lagrange multiplier with 3 variables, which is the same as 2 variables, except that now you have 1 more equation and 1 more unknown. So please be sure to do the example yourself, okay? And then we'll move on to the next page. Now on section 5.3, now we have 3 variables. Okay, now we have 2 constraints. There are 2 conditions to it. Now what? So we know how to do this in the past too. Okay, the way we did it in the past to solve this kind of problem is that, for example, we might assume that x is being that there are 3 conditions, we'll plug x equal to x of z from and we'll assume that x equal to x of z and y equal to y of z. Okay, and then plug it into these things to calculate various stuff. For example, we plug x and y into g, okay, and then we get this equation. And we've done this many times. That's why this looks familiar. But please do this again, okay? We'll plug it in x and y into g and get this equation. Similarly, we plug it into x and get a similar equation. Right, and then from there we notice there's the dx by dz and dy by dc from 2 equations, and we need to isolate them by Kramer's rule, with the determinant being that thing. And then so dx by dc is end up being that, and dy by dc equals to that. And then in the meantime, then we also do this to f, okay? Plug x and z, y of z into f, and calculate du by dz, which is equal to this stuff, okay? And then let's look at the next page. And then continuing, we have, so du by dz, we can write it as this, and that's from the previous page. Let me see. Right, the reason this is complicated looking is because dx by dz is a determinant divided by, it's a Jacobian divided by something, right? dy by dc is also that. So when you plug it in, then it looks fairly complicated. Let me flip the page. Equals to this stuff on top. And okay, we write, so a equals to that thing. And then so when you multiply the whole equation through by the triangle, being that the equation equals to 0, so we'll multiply it by the triangle so that we get this symmetrical looking thing right here. Now to solve this equation is this is the same as the determinant equal to 0. because this is f1, okay, minus f2. If you calculate the determinant, that's exactly this equation. So which we can write it as this, the Jacobian. Now, if you forgot how the Jacobian works, it's on page 28 for refreshing. But it basically is you go FGH, okay, and partial derivative of XYZ going, so first row partial X, partial Y, partial C. See, and so that is so that's that. So that's the old way. Now, what do we do with a new way if we have the Lagrange multiplier? Well, we'll pull the same trick, except that now we have not just lambda, we have lambda and then mu, but basically the same plan. Okay, we'll write this down like this: f plus lambda g plus mu h. Remember, g and h equal to 0, so adding it doesn't change f. So we'll take partial v partial x, which and set it to 0, and which that's the same as f. But we have lambda and mu in there, and then we solve for lambda and mu but now we're solving it from a system of equations. So lambda equals to, similarly, there's a determinant here, so that's mu divided by the determinant using Cramer's rule. And then and when you plug lambda and mu into the third equation right here, okay, then we end up being this thing. And when you write it all out. So please do this yourself, okay? This looks a bit tedious, but it's good for you to do this. Well, maybe it's good, I don't know. It refreshes the memory of what we did in chapter 1. I've always found this stuff to a bit confusing, like who am I taking derivative against, who's the partial and all that. So it's good, it's really good to refresh your memory by doing this stuff. So anyway, we calculate lambda, and then so you can eventually equal to this. And what is this thing? This is exactly this same determinant if you calculate the determinant develop it along the bottom row right here. Okay, so f3 times and then minus g3 and so on, and it all works out. So please double check to make sure what I tell you is true, and that's and then we'll look at example D. So next, let's consider example D on page 139. We need to show that the shortest distance from a point to a line in space is the perpendicular distance. Point to line, all right, is perpendicular to the line, all right. So then we have, in vector notation, we have a dot x equal to k and b dot x equal to l together. These are two planes, okay? That's described on page 67. The two planes, so we're using two planes to describe one line, okay? And what line is that? The line is described as A cross B, because two planes, when they intersect, they intersect at the line, right? And A and B are the normals of the two planes. So when A cross B is going to be, it will be the line's direction. Right? Because A cross B has to be perpendicular to both A and B are both perpendicular to the line because the line is contained in both planes. But anyway, so the point is A cross B is not 0. It is important, otherwise your line doesn't have a direction. So let's assume C is some point, okay? And then we're going to write these equations. Remember, A dot x is not a vector function in the sense that it's just a shorthand for A1x1, A2x2, and A3x3 all added up, okay? And so as a result, we are able to write the function v right here, which is which give us, this is a shorthand way of writing a whole bunch. There are 3 equations here. And then when you take the partial derivatives, then it ends up being A1, A2, A3 times lambda, and B1, B2, B3 times lambda. And I have written down a little more extended here. It's basically the same idea here. Okay, we have x1 and this is partial v partial x1, and x2 and x3 are the same thing. Now at this point, we notice our equation is we can just eliminate lambda and mu by simply using finding. Okay, we'll apply equation 7. Remember equation 7 on the same page where it says that the lambda equations is equivalent to this thing. okay, which is partial FGH partial XYZ equal to 0. Now in this, so in this case, then we get, where is it? In other words, this thing, okay, the part when G is the I don't know, A or something, yeah, and then not A, AX, and then H is the BX or B something. What are we talking? Yeah, B is the other line. But anyway, if you plug this thing, apply 7, then we get this particular determinant equal to 0, where A cross B equal to not equal to 0 is this situation. And what is that? That's exactly equation 6. You notice A cross B equal to not equal to 0 means those things cannot all be 0, okay? The coefficients of ij or k cannot all be 0, which those coefficients are exactly this situation right here, okay? And that's when G this exact thing. All right, so then so that condition is satisfied. That means I need to find it. Okay, here it is. And we have, so this is the same, this determinant is the same as AB and x minus c. I just wrote it differently. I mean, all equal to 0 anyway, so it doesn't matter which order you write it in. So this one, we know that the determinant is the same as, now we're back to vectors, okay? It's A cross B dot C. That is, this is the same as A cross B dot C. I think that's on page 64. So that proves that A cross B is perpendicular to x minus c, and therefore A cross B, and being that A cross B is the direction of the line, so then x minus c is perpendicular to the line, and the perpendicular distance therefore is indeed the shortest distance, okay? Yeah, so that's that. So we have come to the end of this section. And for homework, let's look at, for homework, I would like you to go back to page 135, that is in the previous section, and do problem 3. I think that was the only problem we skipped in the previous section. And I would like you to do it because that problem, I did try it in the previous section, and it was a complete pain. And it gets so much nicer now that we have Lagrange multipliers. So please apply Lagrange multipliers to problem 3 on page 135. And then the rest of the homework, let's see. I need to find it. Now I notice this section seems to have a lot of review of the past stuff and current stuff, a lot of writing. But please do it patiently. Go through the whole section. Okay, one step at a time. Make sure every single thing makes sense to you. All right. And just because we had it in the past, may feel like, how come I don't remember all of it right away? It doesn't hurt to refresh your memory. Okay. All right. So let's. So here's the homework. First, please do the old problem, which I don't normally do, but that one was such a pain. And also, that one was something about distance in 4 dimensions. I don't remember if we ever had defined what distance in the 4th dimension even means, but just assume the Pythagoras theorem works. That is, the distance is a squared plus b squared plus c squared and d plus d squared, and take the square root, okay? Because we're talking about 4 dimensions here. So just go ahead and apply that, and then use the Lagrange multipliers, which should make your life a lot better. And then after that, then do the homework of this section, which is problems 1, 2, 3, 5, 7, 8, 12, 13, 14, 15, 16. Yeah, I think I got all of it. And when you're done, I want to talk about all of them. All right, now first let's look at problem 3 on page 135. Find the distance for the point ABCD in 4 dimensions to the hyperplane ax plus by, etc. Okay, how would you do that? Well, we'll do it the same way we always do things. It doesn't matter how many dimensions or planes there are. Okay, we just apply the same trick. Now the problem is, how is that going to work out? But now that we have Lagrange multipliers, we don't have to do a big division that will that about wore me out. Okay, I tried it. I could not get to the end, not even with calculators. It was just such a horrendous pain. I decided to forget it. Now but now the problem is looking really, really peachy. Okay, now, so we have f, of course, the distance squared, which is each thing minus the other things squared, okay? And then g is the plane, and then we are going to do the same trick, okay? V equal to, now we have 4 variables, x, y, z, u. We'll apply all, use the Lagrange multiplier. We haven't done the four variables, but I'm sure it's all the same, right? Because we have only one constraint, so we only need lambda. We don't need mu or anything like that. So we just have more equations. We'll calculate all this stuff. See, everything looks exactly the same. So very soon, we by staring at this stuff, we realize lambda equals to all these things, right? And then I decided to call them t. Is lambda this? Yeah, lambda is 2 times. Anyway, I decided to call them t for some reason. Well, whatever. And then in the meantime, so then we get x equal to that, y equal to that, and so on. And then I'll plug it into g, which then give us g equal to this thing, which equals to the other thing. And then, give me a second, I'm confusing myself. Okay, so I figured that out. I guess what that is, then g equals to that whole thing equal to 0, okay? Which means, let's see, okay, let me get rid of the equal sign here. All right, so then as a result of that, because that equal to 0, that means this part, okay, where I sum up all the terms with t in it. Remember, t is this thing. So all the terms with t in it, and then the other side, throw the other side all the stuff that doesn't have t in it. And then the distance squared is, what was distance again? Is x minus a squared. What is x minus a squared? It is a squared t squared, right? So I put it right here. Similarly, y minus b squared in the distance formula is b squared t squared. So I get all this stuff. So that's distance squared, which is, we can factor out the t, which is equal to that, now based on this thing right here, what is t? T is equal to that divided by that. What about the negative sign? Let me check some more. Actually, we don't care about that negative sign because t is being squared. So here's t, and t equal, we'll pull the entire t over here squared and plug it in here, okay? Which is equal to that thing squared divided by that thing squared, and then multiplied by, and still multiplied by this. So which means you have just one left, okay, and 2 of them on top. I mean squared on top, and just the thing itself left, and that's distance squared. So the distance is taking all the stuff square root, which is just this one, which is exactly the right answer. Okay, the problem 3 doesn't have an answer at the back of the book, but I have independently checked this from some other solution. And well, there's another way of doing this that's much faster, but we are doing it the maximization way. So so that is this. The other way is using the vector way, which is that is, we do it the same way as if it's a, what are we doing here? A point? Is this a point? Yeah. The point, the distance from point to plane has a similar formula in 3D, which we already learned, and applying it to 4D will it gives us this result as well, which is how I know that it works. But using my maximization method is very tough. In the sense of being incredibly tedious, especially when it comes to taking partial derivatives, unless you use the lambda trick, which isn't near as bad. See, this looks much better. The original, let me show you the vector trick. Okay. Now here's the vector trick I did back then. Let's see, so here's the vector trick. You do the subtraction and then do the dot product, and then, well, this is this is dotting. What are we calculating? The distance? Well, whatever. The point is, you take the dot product of the normal of the plane. Yeah, that's what it was. That's right. And then and that will give. See, it gives this thing right away, and that is the right answer. So, and I also Googled online. So anyway, as you can see, this is the shortest answer, right? And when I tried to do it the long way, and I had, well, you don't want to see this. trust me. And but anyway, so that's the original method. But what we are doing right now, of course, we're doing maximization. So we want to try out the trick of the Lagrange multipliers, which is longer, but not horribly longer. So that is problem 3 on page 135, an old problem. And yeah, now let's do problem 1 of our current section on page 140. The problem 1, I think, is fairly straightforward. Okay, I'll just show you how I did it, and then you can right, here is the entire page of stuff. You just follow the formula and do the v, right? And then you come up with some stuff, and you have to calculate lambda, and then you notice that x is equal to plus or minus y. Now, if that is the case, then you continue to work on it, and you have to reject one answer because it's not minimum. And then after some not really a whole lot of work, then you figure out that the distance is eventually equal to this thing, where we have y and x and z right here. So you can calculate the distance, and here's the distance. Now, the book also wanted you to calculate the cosine of the angle. I'm not sure why, but okay, here's the calculations for the cosine of the angle. Remember, the cosine angle is the dot product divided by the magnitude of somebody, right? This is on page, I don't remember, but it's maybe 67 or so. And so anyway, so the angle is equal to that. That's all we need to do. So that's problem 1. And then problem 2 is, where's problem 2? Now let me find it. All right, next let's consider problem 2. That is, let's see. Problem 2 have a basic problem. Okay, what I did is I did it in problem 2 didn't have anything unusual about it. You don't have to. It doesn't matter which one is independent or dependent. There's no trick. So what I did is I did it the old way, like without Lagrange multiplier, which is which I was able to find the answer. Then I tried to use the Lagrange multiplier here, okay, and it wasn't that much better, really. Maybe even worse, but no better. So it's basically the same as I came up with the same solution. I mean, not solution, but the system of equations as the using the old method. So I guess problem 2 is just to tell you that Lagrange method isn't necessarily any faster. It's just that it only works sometimes, especially for unusual problems, that where who's independent and who's dependent is a big deal. I will finish this section in the next video.